Welcome to today's Explainer. Today, we're acting as cosmic detectives, and we're investigating a massive cold case from the absolute dawn of time. We're looking into a period of the universe that is utterly foundational to our existence, yet notoriously difficult to study. So let's journey back billions of years and try to uncover some of the hidden truths of the cosmos.
Okay, let's just dive right into this mystery. Think about this for a second. The very first stars that ever lit up our universe, what astronomers actually call population 3 stars, are completely gone. They are totally extinct. They lived fast, they died young, and they left absolutely no direct visual evidence behind. So we're faced with the ultimate scientific paradox, right? How on earth do you study a star that died 13 billion years ago?
Looking at the cosmic timeline here really illustrates exactly where our missing suspects lived. Right over at the beginning, we have the Big Bang, which was followed by a period about 380,000 years later known as the Dark Ages. Back then, the universe was just this dark, expanding sea of neutral hydrogen. Then, around 200 million years after the Big Bang, those incredibly massive first stars ignited, finally breaking the darkness. They were the pioneers, literally the very first light in the cosmos. But notice that huge gap on the timeline? They vanish completely, long before our modern galaxies even start to form.
So, the missing first stars, where do they actually go? Well, if the original suspects are completely gone, we've got to look at the messy crime scene they left behind. Now, these original stars were incredibly pristine. When the universe was born, there was basically nothing but hydrogen and helium. That's literally it. But these massive first stars acted like giant cosmic ovens. Deep inside their cores, they forged the very first heavy elements. Now, a quick side note. In astrophysics, basically anything heavier than hydrogen and helium is just lazily called a metal. You can kind of think of it as metallic pollution. So when those massive first stars exploded in supernovae, they blasted this very first wave of metallic pollution across the entirely empty universe.
Which brings us to our next section. What is stellar archaeology? Because the early universe was now polluted by those initial explosions, the very next generation of stars ended up forming from that slightly metallic gas. And since we absolutely cannot observe the original stars directly, we have to borrow a trick from earthly archaeologists. They don't go out looking for living, breathing dinosaurs, right? They dig for fossilized bones. In the exact same way, stellar archaeologists have to dig through the chemical signatures of the oldest surviving stars. We're looking for the direct descendants of those first stars, that second generation, because they still carry the chemical fingerprints of those original, ancient cosmic explosions. There's a really stark contrast to keep in mind here. Our sun is a modern star. It's incredibly rich in heavy metals. Basically, it's heavily polluted by countless generations of dead stars that came before it. But if we want to find the direct descendants of the very first stars, we have to hunt for the absolute cleanest, most metal-poor stars in existence. We're looking for stars that have almost zero heavy metals, because that tells us they formed from the debris of just a single, first-generation star.
So let's talk about searching for metal-poor stars.
To find these elusive relics, we actually have to move our dig site out to the vast, chaotic halo that surrounds the Milky Way. When they're hunting out there, stellar detectives are looking for some very specific chemical clues. They want extremely low iron levels, obviously, but surprisingly, they often look for unusually high carbon. You might be wondering, why carbon? Well, it's because the very first stars likely ended their lives in surprisingly low-energy supernova explosions, so the really heavy iron fell right back into the black hole that formed in the center, but the lighter outer layers of carbon, those were blown out into space. And crucially, we're also looking for a distinct lack of what we call neutron capture elements, because those normally take a very long time to form in the universe. And you know what? This insanely specific search actually pays off. Finding a star like SMS J1605-1443 was an absolute game changer. Discovered out in the galactic halo in 2018, this ancient relic has an iron level that is, to put it into perspective, barely 1/1,000,000th of what we see in our sun. Literally a millionth. It is one of the most metal-poor stars we have ever detected. This single, solitary star is a direct chemical fossil, giving us a practically perfect snapshot of what the universe looked like right after a first-generation star exploded. Moving on to Segue 1, the fossil galaxy. Because honestly, finding isolated stars is literally looking for a needle in a cosmic haystack. But what if we could scale the whole thing up?
Behold Segue 1, discovered about 75,000 light-years away from us. It is an ultra-faint dwarf galaxy, and I mean incredibly faint. This entire galaxy shines only 340 times brighter than our sun. 340! Our Milky Way has hundreds of billions of stars, but Segue 1 is so elusive and so heavily masked by a massive halo of dark matter that it's practically invisible. In fact, at first, scientists were actually arguing about whether it was even a galaxy at all.
But comparing its chemical footprint highlights exactly why Seg 1 is the ultimate fossil, the absolute crown jewel of our investigation. In a normal dwarf galaxy, star formation is a continuous process. You eventually see a drop-off in alpha elements compared to iron, purely because later Type 1a supernovas pump a ton of iron into the system. You'll also see neutron capture elements popping up from older intermediate mass stars. But look at Seg 1, there is no alpha to iron drop-off. It is completely lacking in neutron capture elements. Its star formation was shut down instantly, essentially freezing it in time right at the cosmic dawn.
So unlocking the cosmic dawn, why does finding this one microscopic chemical signature matter on such a macroscopic scale?
Because it actually solves a huge cosmological cold case known as the missing small galaxies problem. See, for a long time, computer simulations of the early universe predicted that our Milky Way should be surrounded by hundreds, if not thousands, of smaller dwarf galaxies. But when we actually looked up through our telescopes, we only saw a handful. It looked like our theories were completely broken. But Segue 1 proves those computer simulations were right all along. The galaxies are actually out there. They are just ultra-faint, heavily masked by dark matter, and their star formation was violently snuffed out by the explosive deaths of the universe's very first stars.
Which leaves us with this totally thrilling final thought. If Segue 1 is just one survivor of this ancient era, how many more of these invisible ghost galaxies are silently waiting in the dark matter halos right above our heads? As our next generation telescopes start turning their incredibly sensitive eyes to the deep dark, we are on the verge of mapping an entire unseen graveyard of fossil galaxies. They're out there, quietly holding the true story of our cosmic dawn, just waiting for us to find them. Thanks so much for joining me on today's Explainer, and keep looking up.